Welcome to the NASA series Exploring the Moon, where we take a behind-the-scenes look at the preparations for humanity's return to the moon.
And in order to take these samples on the moon, you need something to pick up the sample with. The spacesuit, you can't just walk around and pick things up by hand, so that's why we make geology tools to help you collect the samples.
Two other tools, some of my favorites as geologists, right? The rock hammer, and we have a chisel.
All right, and we've got a good clean chip sample right here.
Hi, I'm Stephanie Cipolla, and in today's episode, we have the pleasure of meeting with Holly Newton, a lunar tools expert. Welcome, Holly. Thanks for being here.
Hey, Stephanie, I'm glad I could be here.
All right, so let's talk tools. We have geology tools here. You've brought a lot with you today. Why do we even need geology tools? What's the point for the Artemis missions?
So the intent of Artemis is to go back to the moon and take geology samples and then bring them back to Earth for scientists to study. And then they can learn more about the moon, figure out what resources are on the moon. If we want to build a lunar habitat, what resources can we use? And in order to take these samples on the moon, you need something to pick up the sample with. The spacesuit, you can't just walk around and pick things up by hand. So that's why we make geology tools to help you collect the samples. And we work with scientists to help figure out how do we not contaminate the sample and keep that sample integrity as we're taking it and bringing it back to Earth.
So we've been to the moon. Apollo went to the moon. They did geology tools. Are you doing new tools for Artemis? Are they the same?
So yes, we are doing new tools. So during Apollo, they actually did not have the same tools throughout all of the Apollo missions. As they learned more about the moon and figured out how to take samples, how to maneuver in their spacesuit on the moon, they would change the tools and make it easier for the astronauts. So when we were looking at what do we need for Artemis, we first looked at the last Apollo mission and figured out what worked well, what types of samples did they take, and what maybe could be improved on. So one of the things we look at that's different is manufacturing techniques. Okay. There's been a lot of growth in that area since the Apollo days. So we look at, for example, on the table here, the tongs right there is an Apollo tongs. You can see on the top of that, there's these little tines and they're all individually connected. So for Artemis, we tried to look at how can we make that simpler. So the head of this tool, it can be made out of one piece of metal. It's easier, simpler, and more cost effective.
Oh, nice. Okay,
so
great.
That's one thing we look at. We also look at the environment.
Okay. What's different between the Apollo environment and the Artemis environment?
So Artemis is going to a different location on the moon than Apollo. They're going to the lunar poles. And at the poles, it gets really, really cold, especially in the areas that aren't lit by sunlight at all. They get exceptionally cold. So we have to think about that with the tools. How do we make a tool that can withstand the cold? And how can we preserve the samples? So in some of those areas, there are these things called volatiles. And it's this chemical that is in a frozen state in the sample. And if you heat it up, it's going to quickly turn into a gas and evaporate away. So we want to keep it in that solid state so that we can analyze it when it comes back to Earth. So we have to think about temperature a lot.
Okay. So does the temperature affect the design of the tools?
Yes, absolutely. Yep, it affects what materials we pick and what containers we use to store the samples.
Okay. Do you have any containers today?
I do. I have two.
All right, let's look at those.
So one of them is a sample bag.
Okay.
So this is the type of bag that you would just put a rock sample, or if you took a scoop of soil, you would put it in here. Yep, so that's an Apollo scoop, so you can see the difference between the Artemis one is a lot bigger, so we can take a bigger sample.
Look at that. And heavier.
Yeah. Kind of the consequence of being bigger.
Okay, and it has a whole hinge right here. What's this all about?
Yeah, so this is...
I'll let you show me.
Yeah, this is a way to help the astronaut angle the scoop in a way that's more convenient for them. So you can press this button and
nice.
change the angle so it's easier to scoop up a rock and put it in your sample bag.
Okay. And then why would you need so many sample bags? Can't you just put them all together?
So to put them all together, it would, one, be a very heavy bag.
Oh,
It could rip through the material. And you could also have issues storing it and contaminating things. It's easier for the scientists to be able to say, I'm going to pick up this sample from this location. So that's another thing. If you took two completely different samples from, this one was from a boulder on this side and this was miles away, you aren't going to be able to compare where the sample was. And so the scientists really want them separated so it's just easier to analyze at the end.
That makes sense. So when you're doing samples, you have the bags that you take them home in, but you have all these different shaped tools here. So why do you need so many different types of tools?
Each tool has a different purpose of what type of sample it's supposed to take. So the tongs here takes float samples. So those are like loose rocks that are just sitting on the surface of the moon. The scoop tool can take a big scoop of soil and just loose soil. We have also a hammer and a chisel.
That's a serious tool.
It is a serious tool. And so you can use the hammer for taking chip samples. So if you have like a really big boulder, we can't take the whole boulder home. It's not
Sure.
possible.
Right.
So we would hammer it and get a small chip of it and then take that home with us.
Okay.
And then the other one you could use is, this is a rake. And you can use it to get small pebbles out of dirt. So you would kind of scoop it up, shake it around to get the loose stuff out.
And then just take home the bigger rocks that didn't fall
Exactly.
through your rake. Okay. And I
then-
noticed that in that one, when you had it in your hand, it has the same mechanism.
As
Is
the
that
scoop.
coincidental or is that intentional?
No, it's intentional because it helps you to angle it in different ways because every astronaut has a different preference of what's easier to hold. There's different techniques. So like with the scoop, one of the techniques for sampling is to make a trench so you can dig a little deeper and get a deeper soil sample. And so sometimes you have to angle it in different ways. And so the mechanism is the same.
Okay.
Just to make it easier and for dust reasons. So on the moon, there is a lot of dust. So the top layer of soil, it's very fine. It's like powdered sugar, but it's also very sharp because there's no erosion on the
Like
moon.
shards of glass.
Exactly.
Right.
Yep.
Right.
And so we have to think about when we're designing mechanisms, how do we make it so it's not going to bind up or break the tool and then make it difficult to take samples later.
Nice. So what is this you have on your lap?
So this is the last type of sample I haven't mentioned. This is a drive tube, and the intent is to take a core sample. So what you do is you use your hammer and you drive it all the way into the ground, and then when you pull it back up, you get this layered piece of different geology at different depths. And this is one of the prime places where we might find volatiles that could evaporate if we heat it up. So we want to be very careful with this type of sample and to keep it cold.
So how would you take home a core sample? Do the astronauts have to pull that core of soil out of this tool?
No, that's a great question. So the curation team on the ground will do that. So they will put it in the ground, pull it back up, and this is actually designed so it kind of keeps the soil in there. They'll put a cap on it and then
Okay.
put it into another container to kind of keep it cold and keep it all contained to
Okay.
bring back to Earth. And then the scientists have a special tool that pushes the sample out so they can see what the different layers are.
So do the astronauts have to store the samples in a cooler of sorts? Because you're talking about the temperatures and the volatiles. It seems really important.
Yeah, that is one thing that is being looked at because in some cases, like maybe not every sample we need to keep all the volatiles from, but there might be some that you
Okay.
want to. So that's definitely being looked at. Are there containers to keep it cold? Do we just need pressurized containers to keep the gas in? Because another problem with gas is not just losing that part of the sample, but it's also could be toxic if you release a lot of gas in the cabin with the astronauts, it, depending on if it's ammonia or some other chemical, it's not very good for their health. So we try
definitely
and
want
keep
our
them
astronauts
safe.
to come home safe, right?
Yep, absolutely.
Okay, so you have one other tool over there, the red hammer-looking thing. What's that?
So this is actually a tool just from a hardware store. This is
Okay.
what we would use on Earth as a
Okay.
hammer. And there are some differences. So something I get asked a lot is, why couldn't we just bring this to the moon?
I was just going to ask you that. Why can't you go to the hardware store and take the same tool?
Yeah. So there's a lot of different factors that go into designing a tool. So first is materials. So there's a couple different reasons for that. There, you can see here, this is like a rubber
Nice
hammer.
grip surface. I have that in my garage.
So the cold environment of the moon, this is going to become brittle and break, and your tool is going to fall apart.
Okay.
And depending on the type of metal, it also might become brittle and break, or it might deform and not actually do the job of chipping a rock sample. So that's one thing.
Okay.
And we also look at contamination.
Okay.
So we work with scientists to figure out, how do we maintain sample integrity? And you have to touch the sample with something. You can't pick it up out of thin air.
Sure.
And so we work with the scientists to figure out what materials do we not expect to find on the moon, so that if they see in the sample afterwards, they see, oh, there's this metal shaving, they can say, that was picked up with this tool, and I know it was this material, so we must have brought that with us.
Instead of finding that material on the moon.
Exactly.
Oh, that's really important. I can see that. Okay.
So
Nice.
yeah, so materials are one thing. Also, designing a tool to be compatible with a spacesuit. So in a glove,
Oh, yeah, you brought gloves today.
yeah.
All right, let's check them out.
So these gloves, these are unpressurized gloves, but if you put
Okay.
it on, you can
They're pretty
already
heavy.
tell. Oh yeah. But
Okay.
you can already tell that this is like wearing a winter glove. It's pretty bulky. And when
Yep.
it's pressurized, it's even bulkier. It's like wearing a balloon on your hand.
Right. So every time you move your hand, you're working because you're wearing this bulky glove. But then how does the pressure play in with your hand?
So when you're moving against pressure, so it's like you have to put force into closing your hand. It's like squeezing
Oh.
a stress ball.
Oh, goodness.
And if
Okay.
so this tool has a really thin diameter. If you have to grip this really tightly for like a 6-hour spacewalk,
Right.
that's going to get really tiring
Okay.
really quickly. And we want to make sure we don't tire out the astronauts, because they can do more. They can collect more samples. They can walk further if we don't wear them out.
Sure.
So we
sure.
have to think about, is there an easy way to hold things?
Okay.
The tongs here for Artemis, you can see, so if I put it in my hand that doesn't have tool, it looks pretty big.
It does look oversized, right?
But as soon as I put it in a gloved hand, it's got this, it fits pretty nicely.
You've consumed the whole space where the fingers go through in your design.
Yeah,
Right,
and
yeah.
also what I can do is I can leave my hand open and still maintain control of the tool without having to squeeze it closed.
Did they do that in Apollo too? Oh no, if I leave my hand open, the tool will fall right out of it.
Yeah, so we're constantly looking at, when designing tools, how can we
Okay.
make it easier for an
Okay.
astronaut?
Well, and now that you've said that, looking back at what are these, the scoops that we
Yep.
looked at earlier, I can see that the new scoop, your Artemis scoop, it has a bigger handle
Yep.
than this one. This is a much skinnier cylinder. Now, what about the shape? Yours isn't a cylinder handle anymore. Is that significant?
This is actually a shape that we used from an existing International Space Station tool
Oh.
that astronauts just liked the shape. It was easy to use in a gloved hand, and then we added this part on the back to kind of help brace your hand against it and just make
Okay.
it easier.
Nice.
And then to make it even easier, so these are kind of small. So if they have to bend, they have to really like bend down or get on their knees to take a sample with this. We made a tool called an extension handle, which they also used in Apollo.
Oh, nice.
And basically it just adds length to
Okay.
this so that they could take a sample while they're
Is
standing
that
up.
what that little button is on the end?
Yeah, that's to interface with
An interface with the extension tool.
handle.
Nice. Okay.
I was recently in the rock yard with astronaut Zena Cardman, where we were working with these different lunar tools.
I would really love to see that video.
Let's show it.
Hey, Holly. I'm Trevor Graff, a geologist here at the Johnson Space Center and part of the Artemis science team. I have a great privilege to be out here with astronaut Zena Cartman. So what I thought would be interesting and fun to do today is to step through some of the sampling procedures. So if you're game,
Yeah.
let's do it.
Absolutely, let's go for
We
it.
have a couple of rocks here.
Nice, yes.
Some that are like the moon. So we have a dark one that's kind of like the mare of the side of the moon, or that dark area that you see when you look up at the moon in the sky. And then some a lighter rock that's like the lunar highlands. And so this is like the South Pole where we expect to go with the Artemis mission. And so I say we go after a sampling procedure on that white one.
All right, let's do it.
All right. So as you know, this would be attached to your suit, and so you want to talk through some of those things that would be attached to your suit and what their use is?
Yeah, so it's great to be able to be a little bit hands-free. When you're working in a pressurized spacesuit, it's actually a lot more difficult than just being in shirt sleeves, and so you really have to have access to everything that you need, much like you would be wearing a tool belt for doing any kind of project here on Earth as well. So we have these fittings where you can actually take the tools on and off and place them either elsewhere on your tool belt or actually on this tool cart.
Awesome. And this is one of the other things that would be attached to your suit or somewhere that is proximity for easy access. You want to talk a little bit about the sample marker?
Yeah, sure. So this is a sample marker, which is in some ways self-explanatory, but it's actually got a lot of really great features. So this one, we'll call it sample marker Tango. I would pull this out and place it next to my sample of interest. We've got this nice arrow that we can use to point at whichever part of the sample we're taking. It's on this long handle because when you're in the suit, it's pressurized and your mobility is restricted. So you don't have quite the same ability to kneel down and bend over that you do when you're just like you and I are here today. And so that handle helps you not have to bend over quite so far. We've also got this here, which helps us calibrate the colors and the light of the imagery that we're taking. And that's actually a really important part of the data that we're getting from these images. And it serves as a scale bar as well. So lots of different uses for the sample marker. So here, we'll place sample marker Tango next to our sample.
Awesome. So sample marker Tango, like you said, is super important for geology and for capturing that context with the scale and the sample marker, and then capturing the photos as well. So if you want to go ahead and take pictures of sample Tango.
Yep, absolutely. Yeah, and so coming up to this sample, of course, like Trevor has taught me well, we would be taking lots of imagery of the context as we're approaching the sample. What's around the sample is really important as well. And then you'll notice I'm taking, or pretending to take photos, not holding it up to my eye like you normally would, but down here and away from me. And this is because I have, in a real spacesuit, I would have a big visor bubble, and so I can't actually get the camera close to my eye. But trying to get images from multiple angles really helps to capture every different side of this sample. We can actually recreate some stereo imagery if you have images from different angles, and then backing away to get a little more context, and closer in to get a little more detail.
Awesome. The scientist in me loves to see that type of context because those pictures are almost as important as the sample itself. So great job. And that's the type of thing that we've been practicing at the MBO as well.
Yes, absolutely.
So we have two other tools. Some of my favorites as geologists, right? The rock hammer, and we have a chisel. And so this hammer is a little bit heavier for the 1/6G of the lunar surface. And the chisel helps us, while we're in that pressurized suit, put the force where it needs to be a little bit easier.
Absolutely.
And so let's get on our safety goggles.
It's a great idea.
And I can hand you the hammer and chisel. And practice taking a piece of that, what I would call is a breccia analog that we're using out here today. So this is a piece of concrete, but it's very much like what we might find at the South Pole with a piece of rocks, a bunch of little pieces of rocks that are welded together, a lot like what we found at Apollo 16 landing site.
Yeah, right on. All right. So when you're in a spacesuit, it's really important to remember, number one, you don't want to hit your own visor, but number two, it's actually really hard to get a good big swing with your arm. And so a trick that I learned from Trevor is that using chisels is really helpful. So we'll actually be using the chisel and then hammering the chisel itself. All right, and we've got a good clean chip sample right here.
If I was also your EVA partner, or that's where we'd want another photo of that chip sample. So
You bet, yeah.
part of the procedure is to get as many photos of that process as possible.
Yeah, the exposed edge of this sample that we broke off is really nice to capture as well.
All right, so we changed locations here. Now we're more in a sandy area, so similar to maybe what we were at the bottom of the MEO, a lot of sand, more representative of that fine-grained regolith we'll expect to find on the moon, like we saw at the Apollo sites. I thought it would be neat to do some other tool testing here, starting with the rake.
Okay.
So the rake here, as you know, is meant to get rid of that fine-grained stuff, but accumulate that more gravel or smaller size fraction samples. And so if you want to join that to the extension handle,
You bet.
we can give that a go here in this regolith bin. So similar to when we did the end-to-end sampling with the rock chip, with the rock hammer, we would do all that type of same thing with the cameras and the sample marker, but just for expediency here, let's go ahead and take the rake sample.
All right, this looks like a great spot. We've got a couple different sizes, textures here, kind of trying to get rid of the finer grain stuff. Got a little bit of larger grains left in our sample here.
Awesome.
Okay.
Go ahead and stow that in the bags. And so you can see how that segregates out those smaller pieces that we can then go ahead and age date. It might have unique minerals or tell us a unique scientific story about the moon. So the first step in the drive tube is, again, all that sampling and pictures that pre-sampling pictures that you take, and talking to the science team about that. But then you'll uncap one of your drive tubes. These are 35 centimeter drive tubes to get you about 35 centimeters below the surface. And you can actually double that up and get twice as deep if that's the request. Like you're doing now, you take that extension handle, it's needed for this procedure, and go ahead and attach it like you are for that 35 centimeter drive tube. So one of the things that's really important here, as we always talk about, is contamination control, of making sure that that tube, doesn't get touched as much as possible, because we're going after the volatiles, those really precious volatiles that we want to learn about on the south pole of the moon. And so we're trying to keep contamination off of that. So fantastic training of keeping gloved hands off of that. And then you pick your location for the drive tube.
Okay.
Get it started a little bit into the surface. And this is where one of your, again, multifunctional tools comes in. I'll give you your safety glasses. Knock the sand off of there a little bit.
Thanks, Trevor.
And so you can use a number of different sides on the rock hammer. And so this is a place where a lot of people like using the side of the rock hammer or the front face of the rock hammer. And you're going to go ahead and strike that a number of times to get the drive tube all the way down to that 35 centimeter mark.
Awesome. And yeah, just like you mentioned, I've found it really, especially when you're tired and you've been working in this pressurized suit for a long time, it's actually really nice to have that broad side of the hammer. Okay.
Awesome.
It's
So
looking pretty good.
about the same number of strikes that it took on Apollo to get the drive tube into the surface. Again, you would take the pictures, so lots of context pictures and stuff like that, and then the next step is to extract it.
Okay.
So now everything's retained inside that drive tube. It keeps the stratigraphy of the subsurface, and we'll go ahead and cap it, so that helps either further retain that material. So there's a cap dispenser conveniently located on your easel. And then we'll go ahead and put it in one of these representative containers. The actual flight containers would be a lot more higher fidelity and be able to hold the pressure that might be in those volatiles all the way back to when we get them to the lab. I see you've already taken out the pin, the retaining pin, and we can go ahead and remove the extension handle. And then a unique feature of these drive tubes is be able to either further retain that material in there. So there's a rod that helps press a little keeper in the drive tube that goes down and makes contact with the top of the material, so that whenever we have the launch and return loads back from the moon, we keep that stratigraphy so the scientists can get the most unique stratigraphy as it was preserved on the moon.
That makes sense, keeping it from getting all shaken up. Cool. All right.
So it looks like you press it all the way forward, and then the final thing is to cap it. And again, with those higher fidelity containers, that'll become even more detailed procedure.
Perfect. That makes sense.
Great job. And you see, just like on the moon, the hole retains its perfect shape, so it would take photos of that. And there's a lot of science even to be had with the geotechnical properties of how the lunar surface behaves.
Absolutely.
All right, that wraps it up here at the Rock Yard. It's been a great day out here with the tools and being able to go through some of those procedures, but absolutely being great out here with you, Zena, and stepping through some of this process with me.
It's always great to work with you, Trevor. Thank you so much for walking me through this process. Can't wait to use these tools for real on the moon.
So we've collected all these samples. You've brought it back to the lander. What's next?
So then at the lander, you put it in a storage container to keep it safe on the ride back to Earth, because there's a lot of vibrations of the vehicle and that could break apart the samples.
And temperature changes too.
Yeah, absolutely. And pressure changes actually from the outside lunar surface into a pressurized cabin. So
Sure.
we
Okay.
put it in a container to store it and keep it safe when we bring it back to Earth.
Okay.
All of the tools, the only things that come in that container are things that are storing samples, like the
Okay.
sample bag or the drive tube that has that big core sample in it. And all of the rest of the tools take a one-way trip to the moon.
They do.
Yep.
They all go to the moon and they stay there forever?
Yep. They just stay there.
Well, do we use them when we go back for the next mission?
Well, we're not going back to the same locations necessarily every time.
Oh, because the science is more interesting when you go to a different destination for each landing.
Yes, exactly.
Okay. What about the Artemis samples? Where are they going?
So we work with the curation lab to figure out how they're going to analyze these samples. That's how we come up with the different containment methods.
Okay.
And so they will go to that curation lab where they will take them out of their containers and analyze them, compare the photography that was taken of the sample, and kind of figure out different information from it.
Holly, thank you so much for being here today and sharing with us your insider look at lunar tools.
Thanks for having me. I love talking about tools.